Today we're going to talk about base 2 and base 16, binary and hexadecimal. But first we better catch up to speed on what it means to have base 10. Our number systems are based on 10, the powers of 10. When we go ones, tens, hundreds, thousands, by the way, they start at the right and they went left because they said so. These are all base 10 numbers. You have 10 to the 0, which is 1. Any number to the 0 power is 1, except 0 to the 0. This is 10 to the first, 10 to the second, 10 to the third, etc. 10 to the fourth, on out. Every place is 10 times as big. Then you have to consider how many things you can put in each place. In this one particular place, there's 10 for base 10. You could put a 0, a 1, 2, 3, 4, 5, 6, 7, 8, or 9 in that particular place. What happens if you want a bigger number? Well, you go over to the next place. You put a 1 here and a 0 there. That's called 10, that you've known since kindergarten. Well, base 2 works the same way. Instead of base 10, we have 2 powers of 2. Kind of rattles your mind. By the way, computers use this all the time. Base 2 binary code. Instead of 10 to the 0, we have 2 to the 0, which is still the ones place. Any number to the 0 power is 1, except 0 to the 0. 2 to the first is 2. 2 to the second is 4. We don't have the ones, tens, hundreds. We have the 1s, 2s, 4s, 8, 16, 32, etc. All powers of 2, everything twice as big going off to the left. The crazy part is, how many different things can you put into there? Well, in base 10 there was 10. In base 2 there's 2. You can only put 1s or a 0. 1s and 0s, binary, digital, anything digital is base 2. 1s and 0s, you might see that in commercials and stuff. Well, how do you represent the number 3? 3, good old-fashioned 3. Well, you can have, well, 4s are too big. We don't need any 4s. You can have 1, 2. As a matter of fact, you only can have 1 or 0. Open or shut, open or closed, magnetized or demagnetized. There's only 2 possibilities, on or off. And then 1, 1. It's crazy when you first look at it, but we don't call that 11. We call that 1, 1. 1, 2. 1, 1 makes together 3. All right? Let's say I have a base 2 number. Base 2 number, 1, 1, 0, 1. We don't call that 1101. It's 1101. A 1 here represents 1 what? 1, 8, because it's in the 8's place. A 4, because that's in the 4's place. And a 1. There's no 2's. There's no 2's, so we don't have any. And there's a 1 there. So that number, 1101, is representing the number 13. Crazy, isn't it? Well, then there's base 16. And you guessed it. Base 16, known as hexadecimal. Base 16 has powers of 16. 16 to the 0, the first place, there's always a 1's place. You've got to have a 1's place. Then there's 16 to the first. The 16's place. It takes a while to get used to that. The one that really gets kids is 16 to the second. It's not 32. It's not 32. It's 16 times as big as 16. Each place is 16 times as big. Well, if there's 10 things you can put in the first place in base 10, 2 things you can put in the base 2, there's 16 that you can put here. 16. Well, we've got 10 of them. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But the trouble is, how do you represent 10? And most kids would say, well, 10, yeah, you just put a 1, 0. Well, the trouble with 1, 0 in base 16 is that 1 now represents 16. I don't want 16, I want 10. If you get too big of a number, you go over to the next place. I've got to have a way to represent 10 in this place. What they came up with was something that's very familiar. A. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. The letter F represents 15. What happens if you want a bigger number? you go over to the next place. How do you represent 16 in base 16? 1, 0. 1, 0, base 16, base hexadecimal. It's a faster way to do base 2. It works in computers and storage and in that data, that hard drive. You see, running the keyboard, running all that information, that computer programming, you don't see it, but it's in there. It is in there, way down deep, and it goes very fast. The processors these days make it very, very fast. Well, let's take the number 50. 50. 5 tens, no ones, 50. How do you represent that in base 16? Well, do you need any 256s? No. How many 16s? Now, in base 2, you can only have 1 or 0. Base 16, you can have 16 of them. How many 16s are in 50? Well, 3. I would need 3 16s, and then what's left over? Well, that's 48. I need 2 1s. So I need 2 1s. 3, 2, base 16 is how you represent the number 50. If you have a number in base 16, let's say AA. It takes a while to get used to AA. AA is a number. Well, in base 16 it is. This A represents 10, because they said so, 16s, which is 160. 10 16s is 160. And an A here also represents 10s, but it's a different place. 10 what? 10 1s. So the number AA in base 16 actually is the number 170. It's how computers work way down deep inside their guts and everything. Then comes base prime. Base prime works a little differently, and you might not know about it from too many other sources because it's fairly unique. Well, if it's base prime, just guess. Just guess what the places are. The prime numbers. The first place is the 2's place. The 3's, 5, 7's, 9 isn't prime. 11, 13, etc. Now this works a little bit differently. You might make a little bit of a note here. It's not like all the other bases. And if you think about prime, base prime, you would think, well, that kind of reminds me of prime factorization. Prime factorization. That's exactly right. Let's take the number 30. Number 30. 3 10s, no 1s. 30. Well, if you do the old factor tree or some other backwards division or the cake method, whatever way you want to factor it, let's see. You need a 3, you need a 2, and a 5. 3 times 2 times 5 is 30. You need a 5, you need a 3, you need a 2. The number 30 is represented by 1, 1, 1. 1, 5, 1, 3. Here's where it's a little different. It's 5 times 3 times 2. Not plus. Not like base 2 where we added them up. Not like base 16 where we added them up. They are each multiple. They're factors. Prime. Base prime. Let's take the number 2, 3. 2, 3, I make a little subscript with P. If I don't make a little subscript, you might think, well, that's 23. Well, it's 2, 3 in base prime. Base prime. This 2 represents, well, it's in the 3's place. It's 3 to the second power. 3 to the second power is 9. 3 times 9. 3 times 2. This is 3 in the 2's place. That's 2 to the third power, because you've got 3 2's multiplied. That's 8. Altogether, that's 72. The number 2, 3 in base prime is the number 72. Very, very important. Each single number has one unique one-to-one correspondence, because base prime has only one way of factoring. And here's a crazy idea, but how do you represent the number 1? How do you represent the number 1 in base prime? Well, you put a 0. A 0. Why? Because 2 to the 0 power is 1. Anything to the 0 power except 0 is 1. You can break everything down into primes. You can change bases. It takes a while to get used to, but that's base 2, base 16, and base prime.